This is a circle. It has a diameter, and a circumference which is pi times the diameter. We can plug in some simple numbers to find that pi is 3.14 and so on. Pi is not a rational number and cannot be shown as an integer over another integer. But what if it wasn't? In history it was rational. Egyptians used 3.16, and Babylonians used 3.125, which was good for their uses but just wouldn't slide today. Here is a circle with the pi we are used to, and here is a circle with pi equals 3.14, no difference, right? Let's look at something where pi's exact value really matters, physics, specifically pendulums. This is the equation for the period, time to swing, of a pendulum. Throughout history the length of pendulum, L for a second's pendulum was 0.994 meters, which interestingly was the original yard. By plugging in the correct values we get a time period of 2, which means 1 second equals 1 second. But if we use 3.14, we would get 1 second equals 0.9995 seconds, which doesn't seem like a lot, but would really mess us up. This means we would lose 4 hours 21 minutes every year, which would crash computers, interfere with computer high-frequency trading algorithms, and destroy our GPS. 3.14 is still quite accurate though. What if we used more incorrect values? Let's use pi equals 2.8 and 3.5. This is what the circles, if you can even call them that, would look like. By the way, these technically aren't circles, but I would like to see you try. Back to the pendulums, if pi were 2.8, we would lose 10% of our time, 36.5 days a year, and with pi equals 3.5, we would gain 36.5 days a year. I don't need to explain the consequences of this. In traditional geometry, pi is the ratio between the circumference and diameter of a circle. But in spherical geometry, pi is different. Imagine a sphere with a circle on its surface. This circle isn't flat, it's curved around the sphere. If we compare it to a flat circle with the same diameter, the flat circle will appear larger. This happens because the spherical circle's diameter bends along the surface of the sphere, while the circumference stays the same level. We can calculate in these two shapes what their circumference is. Whilst their diameter may look different, it is actually constant. And we can measure to find that C1 is greater than C2, so we can tell that pi is not the same in both equations, and in spherical geometry, pi is less than what we think. So, in curved spaces like a sphere, pi isn't fixed, it can change depending on the geometry. So, as we've seen, pi isn't always 3.14. In spherical geometry, it's smaller, and in hyperbolic geometry, it's larger. This shows that math can change depending on the space around us. Thankfully, however, pi is what it is in our geometry, so we can have GPS continuing to work.